knows about what Pavilion cases there.
Okay, so thank you, Dave. Thank you, Chris, for the all right. So this is the pipeline. First of all, speak a little bit about what the defined inequality is, possibly defining over here. And then towards the top, set some outlines of generalizations of the inequality and how you might prove it. And then outline partially. All right, so this talk is based on going to work with complex and partly what Richard went through over the past year or so. And a couple of our papers are on the archive, one is here, and then the paper with Richard is in progress. All right, so let me begin by talking about the defined inequality. So this is something that can prove can be taken exactly independently by using methods of geometry and by Yao, so an approach is probably represented by detectors. Good says you have a surface, complex surface of it, then you have this inequality of so there's a nice exposition in this group. We have this group is really short, it's about 12 pages. But there's a simplified version of it in the book by Bart. And this is the famous picture of the geometry plane. The coordinates are a little bit different. I'll explain that later. But I stole this from John. So this is the known region for minimal complex surfaces. Then formed by the question about, well, how is this region populated by symmetry to form a level of the So I should say, in addition to the proofs by Yao and Yoka, there's also an interesting one by Carlos Simpson. Basically, a corollary of this 1970 pieces where he generalized the case equations that were invented by Michael Hitchens. And he has a proof which does use TDE, uses pairs. So this does the approach I'm going to accept, although his notion of pair connection and tension is very different from partnership. And of course, or in the same setting of the complex. It does rely on an inequality that is much simpler than the inline inequality. And it's known from differential geometry for a long time, so-called Bogomola inequality. Simpson relies on clever right. So we're interested in describing the generalizations that applies to a broader category of inequalities. In particular, but the attempts of the broader category. So for that purpose, I'm going to rewrite the inequality slightly and also introduce some terminology which is right. I should also say that you stood speaking of rumors, plot that is good plot. So not taking 2 hours up here. Somebody's going to that's all right, thank you. Okay. So these are purely topological numbers, C1x squared, defined in terms of Euler characteristic signature, and this so-called holomorphic Euler characteristic, also defined in terms of Euler characteristic signature. And next is standard Fourier manifold. If it has these attributes, closed, connected, oriented, smooth with odd p plus, V1. All right, with that terminology, we can say the generalization of the theorem conjecture that if you have a standard format hold of cyber rings like non-zero invariant, then this inequality holds. And this, the way I've written this inequality, the way it's written down, it's equivalent to the one written and if you're looking for various places where this conjecture is stated, it's stated in the downward stitches, more or less for symplectic core manifolds to be connected. Symplectic core manifolds by von Stern, perhaps a few other places as well. So, the reason that we stated conjecture in the way that we did is that we know from Cliff that symplectic core manifolds have cyber rings of China. There are also invariants, there are also core manifolds of non-zero cyber ring invariants that are not symplectic core manifolds. So it makes sense to break the conjecture in terms of cyber ring invariants rather than symplectic core manifolds as it is reality. So different attempts to both either prove or disprove this conjecture for many years. Attempts to disprove it involve examples, and all the examples that are known, they apply below why, these are on below. So there are a whole bunch of people who have done work that's related to constructing capture examples. There are also been positive attempts to capture cases. So LeBron has been rescue proof using cyber working areas, like it's just a case of format. So that's the other kind of proof of the modeling technology calls using a generalization case, equations from Hitchin, and then one to LeBron involving cyber working invariants. So putting those two things together and also an observation on this plan, is there an degree of so the generalization is based on the following conjecture, really a case theoretic one, which helps us right. So we're in a setting where we have a region, right, and we ask about the existence of an anti-self-build connection on the associated S&P bundle, which satisfies a basic formula. So if it does, as we'll see in a moment, then in this favorable setting, this will imply the line. So here, what we're effectively asking is to produce an anti-self-build as a big connection in the bundle with small instances. So to get tested with results from long ago in case theory, one of the most famous results was the production of the existence of connected when based on number disappeared. So the opposite, right? As the existence of number is strange. So to see why this conjecture might be useful topologically, I need to introduce or recall the definition of the modular space of connections, which is subject here, and just connections on this region here, bundle. And it has a well-known effective connection model, which we're going to express in a certain way. Deviation, but for the purposes of the basic or boundary, and also the in mind in mind. Of course, the space could be empty, but the expected image still makes sense. So one of our goals is to show that this modular space for this very particular choice topology and bundle is not empty. And if it's not empty, then we'll have a smooth manifold of this thing. All right, so what does that advise? So what it advises is that if the expected dimension is non-negative, and in a setting where the space is lower bound for conjugation for holes, plug in that value of D1, and you can you recover the line. So this little outline is intended to give you the flavor of why you see it as actually bundle topology. All right, so as soon as you phrase a question in this way, in terms of existence of solutions to the self-total connection, so it begs the question, well, does this include desire? Certainly, we know from ground that exists various Lakeside. You can get some traction from that. You can also know from our experience with the molecules and techniques, various models of areas that exists in sort of solutions to the ASP gateway may have something to do with this. So first of all, the difficulty in proving this vector to distance of ASP connections because you're asking for distance of ASP connections. When it's a time numbers, all in the opposite direction. So instead, the way that we're going to try to prove the existence of the connection, that's by doing more street not a big model. So if you remember from the 90s, that you had proposed the moduli space not a big model, model. At the type of board, so that 12 big moduli spaces by the so we're proposing to do some version of more security on this moduli space of not the tricky part is to say sustainable. We're going to use to be set up as very use implementation in 80s, where we describes more security we developed on moduli space of these model for years. And by choosing the rank and the degree of this level or this intermediate vector level of time, we were able to array these moduli spaces. So all computations are in terms of spot indices in the equal sense, manifolds, more function chooses similar adopted small spot computations. So it works pretty nice. So we're looking to regulate what constituents in the setting of the moduli spaces. I'm not going back. All right, so I'm not going to explain the non-linear model equations that would time but I'll simply say that there are a set of equations which are formulated by a similar equations. Here, a section of the Bible. The A here is a direct operator like the only difference is that the bundle B is a rank to higher. In other words, it's we can form a moduli space in a way that's reminiscent of all these theories. It is non-convex because it contains moduli space, not just functional connections. For example, if we set the section here to 0, then we recover the equation. And there's a more subtle reduction of these equations when useful. But we get the moduli space whose dimension representation and has a weak generic parameters type there associated with it that allows you to say that at least a large subset of those moduli spaces. In particular, it has a very useful decomposition. The reason that so it splits up into dimension space, subspace with a section that turns out to be a complement of this moduli space. And then there's a subspace where the connections are useful. They turn out to be a that turns out to be the union of moduli subspaces of And then there's everything else. This moduli space, decorations, star, zero. Star makes connection. Useful zero is second, not zero. And that's the, from a manifold perspective, that's the nicest part. Generic parameters, notice by extension, manifold. So one of the ways which are hypothesis of dimensional format, non-zero side comes in is to show that this moduli space and the star at zero. And there's a picture that goes along with this all right, so more or less this in so many words. But the other thing that's important to remember about these central points is that zero or they are based on the circle actually on the moduli space. So we function that by this. So there's a residual circle left over. And these two types of special solutions represent the circle action. And what does reducible mean? It means a connection respects time of splitting. And if it does, then such when you have a certain kind of splitting, you get a corresponding. Yeah.
If you have not trivial power, great variance.
I don't know. You really want to say we're using yes. So at the bottom, we have the modular space. If you're familiar with these things, paper from the 80s, that's the modular space connectings. And then we have these various spreads labeled modular substrates. They all look like they have dimension 0, not. In HF paper, it would be useful. There corresponds to useful dimensions, but spinner field in this case, direct field not 0. In our case, the sections are necessarily not 0. And the picture also suggests that the critical points come in various flavors, where the which, but it also might be singular, so that's possible. So doing more to the suitable Morse function on this modular space, where we straight more near the swing points, I think that's tricky. And to say we by Morse index get some traction. So what's the work? So we basically copied Hitchin's idea. It turns out that if you read papers by Bradlow and Bradlow, Saveliev, that's very good as a national choice. But we copied Hitchin's idea initially without knowing the broader context. Just take the L2 square on the center. So let me give an outline then under very idealized circumstances for how the program works. So we might temporarily assume that the moduli space is not linear monopoles smooth. You know, it's also attached. These are these assumptions are taken. And that this candidate response function F is actually a reasonable spot with critical manifolds corresponding to the moduli subspace. You can actually do the mirror so in that favorable setting, you can compute the kind of the weight spaces, the dimensions of the positive, negative, and null spaces, the tangent space. You can do this using the issues state or the whole variable there that relates these dimensions two ways there, sort of black, provided you're making that assumption as well. So if this more spot signature happens to be positive of all critical points, those will all decide away from then we've gained what we want. More students exist. So our goal is to try to cover this outline setting for critical points, critical points, not students. Yeah, here's the picture. All right, so the nice trick that the kitchen uses this paper to compute force indices is the following. That is, if M is a Hamiltonian function for a circle action, like then critical point of that function corresponds to basically the circle action. And then the Morse spot signature can be computed as one of the first configurations of corresponding point spaces. So this is particularly useful when the base format happens to be a scalar surface. Then you can show that the moduli space of the module is a complex circle action. And aside from singularities, the case for computing these indices. So these indices in turn, they can be computed in terms of conditions paper just has a condition mention of weight space, subspace, and space. So one of the things that we do in the paper is show that placing the condition on each minus that the virtual distance that means exists down. So this is quite unexplained here. So in the ideal case, H1 and H1 minus that would be the dimension of the tangent space of this first line, or the subspace would be the Hessian data. For a singular point, this quantity is measuring the difference between the negative weight subspace of the receiver and the negative weight subspace between the purity solve at a single. So one of the things that one can tell is that if this is a virtual version of force index, it's positive, then you still have a problem. Just so these idealized assumptions that I made is the flavor of the program. None of them hold that critical points, such with moduli spaces, or no way to say it because it's moduli space. Also, the moduli space is seriously not dependent, but using theory. And it's also in general not necessarily tailored. So if you have a selective space for example, it's not necessarily true that one of those spaces full connections are generally as all right, so there are a couple of ways of addressing the non-compactness. I'm really only going to talk a little bit about one of them. So one thing one might do is give oneself some confidence that the program has is to try to use the gauge series scheme to know the why inequality for applied surfaces. Now those surfaces are necessarily connected. So that means that it's also true that you can use a version like the Hitchy going back from the Yashi correspondence. the number of molecules setting to homomorphic pairs over your complex surface. So this is an extension of the idea that also more includes code would be also as diverse normalization to the modernization. The other way in which one might solve the non-matrix problem is to examine the moduli space molecules for geometric destructive like. All right. So as far as where we are in our program, we initially thought that it was going to be rather quick, but then just kind of seeing the horizons slowly recede into the distance. But we can prove what we need to prove for a large class of points. So in other words, when there's no bubbling, in the case where the form manifold is scalar, and we're mostly done in the case where the form manifold is complex surface type. But the general case is be flat. It's a pretty simple type. That's the future one. All right, so I'm going to very briefly touch on how we do the force theory on singular. I'll skip over a whole bunch of slides because technical. So the key thing to keep in mind is that if you have a C-star action on some nice complex manifold, and you have some complex subspace manifold, then you can restrict the Hamiltonian function from a nice ambient complex manifold to the singular complex subspace, and get some useful information by doing it. So the version of the force theory that we end up studying, at least in the near term, is the following. It says that we're going to extend the definition of the movement index Morse spot function at a critical point on a sliver. The case where we have a critical point of the Hamiltonian function for a circle action on the complex invariant subspace of the manifold of the star action. And there's independent interest in doing this because it's kind of setting provides this engagement. So, beginning with moduli space being something but this extended definition of the force index allows you to consider modular space. And also more generally consider Higgs bundles over scalar manifolds, moduli spaces projective. That happens to be the one that's relevant to us. Moduli spaces that would be with molecules over scalar manifolds, and so on. And it relies on something that's been long known in economics, so called the LPD rule for holomorphic C-star actions. And I'll just indicate the part of the definition. So the idea, roughly speaking, is to replace the role of function by how you define unstable manifold, stable manifolds, and smooth and force theory by these limits of C-star actions. So we have a set of fixed points, and then you can define an unstable manifold or a stable manifold in terms of limits of C-star actions. From this point of view, it began with Young and Carolla, big around until the late 1970s, was then increased in 75. Mostly in the case of smooth space. And some of our work has been to extend that into category parts of it of smooth level. Enough. All right, so that's all I will say. All right, so I'll describe some results that show at least part of this program has some life. So the first thing we want to know is that we can actually construct a useful masonry framework which improve the DUI is on. So that means that we need a modular space. Multiples quickly against a basic principle modular space the collections and the contain some sign of functions. So you can this part point and do in some generality. So if you have a four manifold cyber with a simple height, then it's possible to construct a modular space of molecules with the right properties for the bundle B, the base is always is lower bound. And the expected dimension holds, and this this version of the Morse spot index, what we eventually show corresponds to the true spot index. It's possible. So in doing these calculations, we translate from the B-theory setting to setting of holomorphic pairs. And then by extending various calculations of the random spaces from the nullity space era, that allows you to compute to find a more virtual Morse spot index in terms of the Euler characteristic of a certain information complex that defines the variable holomorphic. And then that Euler characteristic is something that you can. So what we show using these calculations is that, first of all, this virtual Morse spot index is computable using the formula, and also in the setting that it's positive. So in a framework where we use this Morse should be so these calculations, these are all done in the absence of them. In order to make them really useful, you have to imagine. So that's not the part that we general. So we're going to at least outline this where what you have is not very. So that's what we call the test case, where we have very compact connected visible surfaces. So if you remember the classification of compact surfaces from the early days of Collins period, you'll know that you remember that they're classified in terms of black, in terms of higher dimensions, so that it's 4 times. And then there's a finer Budaya-Rodriguez classification that splits up this work groups into subfactors. And you get a table, which is the following, which I stolen from 5 years. It's just following a really nice table here. So remember, we're interested in, so if we look at the last column, we're interested in the case of surfaces where C1 squared is less than times 2. And the only case the table shows you that you really have to worry about is the only, in quotes, the case 10, where you have interval surfaces. Where C1 squared is positive and C2 is positive. So in this setting where C1 squared is positive, it's known that these surfaces are unprotected. That's good for so that's why in attempting to prove that BNY holds for compact, worry about the So, so in that setting, when you have a complex projective surface, we can hope to compactify. So one thing to mention that before we discuss this, there is a version of Whitney's dichotomy for cyber-Whitney manifolds. So if you remember from the early days of cyber-Whitney, cyber-Whitney manifolds have two layers, so-called type 1 and type 2. And it's, for our purposes, it's only necessary to consider, there's a version of this for non-Euclidean manifolds. And we only need to consider so-called type 1 non-Euclidean manifolds on display on the go. So we call these projective vortices in the partial work parallel. So, so here we have here, which is the unitary connection on a Hermitian vector bundle. P is a section of that bundle. And they make these equations. So these are very like, formally rather like the cyber equations of the surface that I described in Dawson's exposition paper around the same year. The subscript 0 means you're taking the trace apart. Lambda omega means that this is kind of the equation product. Omega is. So these equations make sense without the connection of the determinant line product. But if we assume that it is holomorphic, then there's a version of the Ashley card, of the Ashley correspondence, basically the Bradlow, that sets up a correspondence between projective vortices and so-called holomorphic pairs. So what are holomorphic pairs? So particular so-called, I won't give you the definition of stable or polystable, but they turn out to be from Bradlow what are called polystable holomorphic pairs. So the pairs satisfying these equations plus Bradlow's. So the O1 connection del RE on the Hermitian on B, this has to be holomorphic. And the section B has to be. So when E has a rank 2 bundle, which is the what we need to be the manifolds, we have at least a set theoretic bijection between type 1 non-abelian manifolds and these so-called polystable. Now, if you remember from the G-series picture, which I put up on the slide a few times, we're only interested in looking at critical points in the section. The section is 0 and rather than bottom of the moduli space have nothing. Also, around the point where the section is 0, there's a gold ring singularity. So if you cut out that subspace, and that gives all connections or projected vortices, so a section in the whole section, then you get a true morphism in the Lie space, the moduli space of type 1 non-abelian manifolds with vortices with non-two sections, unstable holomorphic pairs with non-two sections. Now, if we focus on this right-hand moduli space of stable holomorphic pairs with non-two sections. This is the nice algebra of geometric compactification. And what is it? So there's been work going back over many years. There was time of Michael Caddy's thesis in the mid-1990s, work of Bradlow, earlier Oscar Garcia Prado, and then in particular by Hygrex and Lane in the mid-1990s on constructing moduli spaces of holomorphic pairs, so-called semi-stable pairs of what they were trying to do was to visualize easier environment where they constructed on spaces of your table, your sheets over operating surfaces. And they essentially adapted those instructions, setting up pairs over calibrating smooth out surfaces. So what these people showed in particular hybrids lane, Koenig element, Lin and Wandel in various degrees of generality, they show that there is a complex projective moduli space following in pairs of G's and vectors that are semi-stable in the sense that Bravo Rama over complex projective surfaces. So their constructions, what they mean by section is not necessarily what we mean by section. So there's some technical differences between their constructions and ours record. But the bottom line is that there exists complexes. So that means you have the following sequence of isomorphisms that is on the right all moduli spaces on the monopoles of the actual section. Next, the moduli space of stable holomorphic pairs of the actual section. And then this nice compact moduli complex projection moduli. And that's all sitting inside the large complex vectors. And these embeddings are also sort of bigger areas. So you're in the setting where you can apply versions of the theory to help you compute define virtual Morse indices, and then using the lock and generalization strategy. So the kind of thing, the reason I emphasize virtual Morse indices is that because we're working in a singular space, we might have some single, and you want to flow, want to follow the gradient flow downwards. So I see format of the should be a negative null vector as negative weight in subspace, and just like follow that. If you're on a singular space, that replace through tangent space and you follow that vector for the vectors. You could shoot off this, you could shoot off at the end of the manifold, but not going down the bottom. So the idea behind the virtual index is probably an mass cost pulling down. Right, so there are a lot of ingredients to combine, but if you combine this Pavilion theory and our methods from our monograph, and then calculations of force indices, then we get a new Bayesian proof of the Y column involved in the compound. So if this, of course, was the only outcome, it would be very interesting. So the very flaws proofs of the hope is that the scheme will generalize slightly. All right. So what are some next steps in that direction? So the key difficulty in the program, or one of the two difficulties in the program, is how to address this. So the ease of compactification works very nicely when the base manifold. That's you get exactly what you need to apply. If you're on a smooth manifold, or manifold more generally, then you have to use some version of Lloyd to construct a suitable local model. Also, not just any. So so we hope that this will lead to applying for generalities, selecting animals. But aside from non-compactness, that's another issue, which is rather tricky. That if you're under an almost complex manifold, well, it's not complex. You use monocomplex technique. So there's at this point you might think about trying to use some of the version of homomorphic approximation. And there's a nice result. At least it was a result for a while due to bias shedding. So pizza groups was these two that solve them. And for a while, you have this really nice thesis result until it became a non-result, which goes as follows. It's now a conjecture. So it says if you're on an almost Hermitian manifold, then there's a sequence of almost complex structures, such that the C0 norms of the 9 concentration. And then, as we've seen in our calculations that we've done, that this could be something that's very useful for homomorphic. It's kind of thing that we'd like to be able to show if you're working over an almost complex form manifold and the modified space also. And one might dismiss this conjecture. Nobody knows whether it's true or false. And, discuss it with many people. But there are examples of form manifolds that are really not complex. We have almost complex structures. There's also a weaker version of this conjecture that's been proved by John Evans using results of Simon on existence. But it's much weaker for various reasons, but one reason is that the C0 norms. All right, so I think this is